Hey, this is Alex from GMAT Ninja. Welcome to our GRE video on conversions and rates. So in this video, we're going to dive into how to convert units efficiently and methodically. We'll talk about rates questions and how to use that work equals rate times time or distance equals rate times time equation. And we'll also talk about how to deal with some of the involved algebra that can come up when you deal with some of the more complex rates questions. Now, in addition to that math content, we'll also go through some problem-solving pointers. One of those would be, if you ever see units in a question, you really want to pay attention, keep track of that throughout your problem solving. If you see inches or feet or yards, there's a good chance that's going to be really pivotal to the question, and if you lose track of it, you could easily go astray. Now, in addition to that, we'll keep in mind, with rates questions, algebra is often your friend. If you see a whole bunch of variables where you would expect to see numbers, the first thing is don't panic. Keep in mind, as long as you're translating that language into algebra, getting some equations that match the language of the question, kind of work through, keep track of the variables and the units, you should be in good shape. Now, we're going to have 8 questions total. They'll start fairly easy in dealing with the fundamentals, but by the end they'll be challenging. Anyone who's even shooting for a score in the mid-160s should find some challenges there. Now, we'll give you a minute 45 seconds for each of those questions. Feel free to pause the video if you need more time. Now, when you get to the explanation part of the video, we'll talk about not just how to get the right answer, but how to get to it in an efficient way that'll be useful for you on test day. All right, let's take a look at the first question. Okay, a steam train can cover 45 miles in 90 minutes. After an engine upgrade, it can travel 50% faster than before the upgrade. So which is bigger? Column A, the time the train takes to cover 75 miles before the upgrade, or B, the time the train takes to cover 135 miles after the upgrade. Okay, so before I dive into calculations, I'm going to think about the logic on this one. So I have a train that goes a certain distance in a certain amount of time, so that would be a certain speed that it's traveling at. But then it gets an engine upgrade and it can go faster. So I'm asked to compare the time it takes for it to travel 75 miles, but that's before the upgrade, or the time it takes to go 135 miles, so a longer distance, but after the upgrade, so it's going faster. So I might say, well, it takes longer to go 135 miles than 75 miles, all else being equal. But in this case, it's going a longer distance, but at a faster speed. So the longer distance would make it take longer, but then if it's going faster, that'll make the time go down. Okay, so I can't just consider the factors and decide which is bigger, A or B, just by eyeballing it. I'm going to have to dive into calculations for this. Okay, so an equation that's often useful when you're comparing, the distances and the speeds of different objects is distance equals rate times time. And there's always going to be units for each of these. In some questions it's miles, in some it's kilometers or minutes or hours for time. So let's keep track of the units as they are in this question. Okay, so I'm given the distance in miles. Okay, so I'll write that. D miles. The time seems to be given in minutes. Okay, so I'll say t is in minutes. Okay, what about rate? Well, rate is the speed at which something is traveling. And this is going 45 miles in 90 minutes. So I'll say, okay, in this question, my rate is in miles per minute. And you can see how the units work out for this equation, because miles per minute times minutes, well, the minutes cancel out and I'm left with miles. Just cancel those. Okay, so let's apply this equation to A and see where that gets us. Okay, so the time the train takes to cover 75 miles. Okay, 75 miles is a distance, so I'll write that down, 75 miles. Okay, the time it takes, well, I guess I'm solving for t, so I don't know what that is. Now, if I want to get t, I can see, well, 75 equals r times t, I'm going to have to get the rate of this train. Okay, rate is in distance over time, or miles per minute in this particular case. Okay, so what's the rate for the train before the upgrade? Well, it's going, I'll just write it down here, the rate is 45 miles in 90 minutes. Okay, so I'll simplify that. That's 1 over 2, or 1 mile per 2 minutes. Okay, great. So I can plug that in for the rate. I have 75 equals 1/2 times t. 75 miles equals 1 over 2 miles per minute times t. Okay, solve for t. I get t equals 150. Okay, and what are the units? Well, this was in miles per minute, so the miles cancel. I'm left with 150 minutes. Okay, so 150 minutes, that's the time for column A. What about B? Well, let's apply a similar approach. It's 135 miles, so I'll say 135 equals r times t. Okay, so I'm solving for t. What's the rate? Well, this is after the engine upgrade. And after the upgrade, it can travel 50% faster than before. Okay, well, before it was going 1/2 a mile per minute. Okay, if I increase that by 50%, that's multiplying by 3 over 2. Okay, so multiply across, I get 3 over 4 miles per minute. Okay, let's plug that in for the rate. 135 miles equals 3 over 4 miles per minute times t. Okay, so if I solve this, I should get time in minutes. So I'll do 135, and let me give myself a little more space for that. 135 miles times 4 over 3, okay, to solve for t. 135 over 3, okay, so that is, let's see, 3 into 135, I get 4, 5, okay, so that's 45. 45 times 4, that's 160 plus 20. Okay, so here t is 180 minutes. Okay, great. So by setting up my d equals rt equation, I can solve for the time for both of these, and I get the time for b is 180, the time for a is 150. So here, quantity b is bigger. Okay, so any take-homes for that question? Well, it's always a good idea to stop and think about the logic of a question before you dive into it, to figure out, okay, what am I trying to solve for? How am I going to get there? And then this equation, d equals rt, comes in handy pretty frequently, when you run into this type of question. And when you're working through it, it's always a good idea, keep track of your units. So you can make sure, okay, I'm actually comparing the same unit, I'm comparing minutes to minutes, so 180 minutes is bigger. And again, that leads us to the correct answer of B. Okay, great. Let's take a look at the next question. Okay, a train traveled at 120 kilometers per hour for 5 kilometers. Which is bigger? A, the time in seconds for the train to travel 5 kilometers, or B, 150? Okay, so in this one, I need to find the amount of time it takes for this train to travel 5 kilometers. So I'm given a speed up there, I'm given distances. Okay, so again, we're dealing with this equation d equals rt. Okay, so I'm solving for t. The distance is 5. Okay, 5 kilometers. So if I can figure out the rate, I can find the time. Okay, I'm told up here it traveled at 120 kilometers per hour, so there's my rate. Okay, so let's plug in and solve for t. So I would get d is 5 kilometers equals 120 kilometers per hour times time. Okay, if I divide both sides by 120, the kilometers should cancel. I'll be left with hours. So let's do that. 5 over 120. Okay, so 5 into 120. Let's see, well, 20 gives me 100. So 24 should give me 120. So this can be simplified to 1 over 24. And again, my units are going to be hours. So that's the time. 1/24 of an hour. Okay, so I might, if I'm rushing, I might say, oh, b is bigger than 1 over 24. But notice they asked for the time in seconds. So units is something you always want to be aware of. Any question, if it comes up, you want to spot it. But specifically on these rate questions, it can often be an important factor. Okay, so I want to convert hours to seconds. So let's go about that in a methodical way. So I know I have 1 over 24 hours. Okay. Now I want to get seconds, right? So maybe all the way to the right, I'll write seconds. And that's what I'm solving for. How many seconds is that equal to? Okay, so to get hours into seconds, let's work there step by step. So how many minutes are there in an hour? 60. Okay, so I'll write 60 minutes over 1 hour, right? Because that's a true statement. There's 60 minutes in 1 hour. And then notice I wrote it with hours on the bottom so that hours will cancel, right? I've got 1 over 24 hours. If I multiply that by 60 minutes over 1 hour, the hours will cancel, and I'll be left with minutes. Okay, let's do that one more time, but convert to seconds. Okay, so I have minutes at this point. I want to get to seconds, so I can do a similar step. I can say there's 60 seconds in 1 minute. Okay, and that should give me the number of seconds. Now, before I calculate it, let's just review the logic of what I set up here one more time. I started with hours. I want to get to seconds. So I'm going to need to have some conversion factors to convert those units. So my first step is to convert hours to minutes. 60 minutes in 1 hour. Okay, these hours as units cancel, and I'm left with 1 over 24 times 60 minutes. Okay, but I want to get minutes into seconds, so I multiply by 60 seconds over 1 minute, because that's a true statement. The minutes will cancel, and I'll be left with 1 over 24 times 60 seconds. Okay, now notice I wrote it all out first before I start crunching the numbers. That's partly so I can check to make sure I actually did it right. I have the units set up to actually give me seconds. But it also allows me to kind of strategically decide what things I'm going to cancel. Right? I might have started off by saying, okay, 24 into 60, and that's okay, but that could involve some annoying arithmetic. So let's see, can we break these down in a way that's, saves us any annoying arithmetic? Okay, so 60 and 24 have a common factor of 12. So I could say 12 goes into 60 5 times, goes into 24 2 times. Okay, that I kind of maxed out 5 over 2. But let's see, this 2 and this 60, okay, 2 goes into 60 30 times. So now I'm left with 5 times 30 seconds, so 150 seconds. Okay, so column A, 1 over 24 hours, but we converted that to 150 seconds, and now I can see the answer to this question is C. Okay, so any take-homes for that question? Well, as always, when you're thinking about a d equals rt question with rates and distances, You really want to keep track of units. It ended up being really essential in this question because they gave us hours, but we needed to convert to seconds. Okay, so unit conversions. What's the best way to do that? Well, start off with the units you're given. Think about what kind of units you want to end up with. And then using the logic of canceling the units, you can set up these conversion factors, right? If I want to get hours into minutes, I'll multiply it by minutes per hour. If I want to get minutes into seconds, I'll multiply by seconds per minute. Set up all that stuff first so you can cancel the units, make sure you're actually getting the unit that you want to end up with. And also, that way you have all the numbers right in front of you, so you can pick and choose what arithmetic you do to find a nice efficient path. And by doing all that, again, we got to the correct answer of C on this question. All right, great. Let's take a look at the next one. Okay, in this question, I'm told that $1 is equivalent to 0.82 pounds, 1 pound is equivalent to 1.16 euros, and also 1 pound is equivalent to 8.19 yuan. And then I'm asked, which is bigger, the dollar value of 1 euro or the dollar value of 1 yuan? So I'm purely in unit conversion territory here. If I can convert these units correctly, I can say which is bigger, A or B. In A, I'm asked to convert euros to dollars. Okay, so remember in the last question, we said start with the unit you're given, think about the unit you want to convert to, and then write down the conversion factors that will logically cancel the units so that you end up with what you want. Okay, so I'm starting with 1 euro. Easy enough. Now, how do I get from euros to dollars? Okay, well, I know the relation of euros to pounds. I don't know, I'm not given euros to dollars directly, but I guess I could go from euros to pounds and then pounds to dollars. Okay, so and maybe just to remind myself, I'm ending up with dollars is what I want. Okay, so D for dollars. Now we said we can go from euros to pounds. So, okay, I want the euros to cancel. Put euros on the bottom, pounds on the top. Okay, now how many pounds are there per euro? Well, 1 pound per 1.16 euros. Okay, so notice it was written as an equation right here, but I can express that, equivalence the same way with a fraction. And writing as a fraction is going to be really useful for canceling the units, converting to the unit that I want. Okay, so I have 1 pound for 1.16 euros. Okay, now I want to go from euros, I have pounds now. I want to go from pounds to dollars. Okay, so I want to go to dollars. So I'll write another conversion factor with dollars on top, but I want to cancel pounds. And I know that there's 0.82 pounds in $1. Okay, so if I crunch these numbers, I'll get the number of dollars that 1 euro is equal to. Now, I'm always wary about doing ugly calculations if I don't need to. So I'm wondering if I set both these up, will I then be able to eyeball them and clearly see which one is bigger? Okay, so let's do the exact same process over here. I'm starting with 1 yuan. I want to go to dollars. Okay, so I want to convert from yuan to dollars, but I can't do it directly. So first I'll go to pounds, then I'll go from pounds to dollars, just like we did with the euros. Okay, so 1 yuan, I want to cancel yuans and end up with pounds. And I have 1 pound per 8.19 yuan. Okay, that got me to pounds, and then I want to convert from pounds to dollars, so I'll write dollars per pound. I know there's $1 and 0.82 pounds. Okay, so let me just go back to these units so I'm 100% sure that I'm getting what I want. So yuans cancel, I get pounds. Pounds cancel, I get dollars. Great. Same thing over here. Euros cancel, I get pounds. Pounds cancel, I get dollars. Okay, so again, really ugly numbers. So maybe I can eyeball this to see which of these is bigger. Okay, so 1 times 1 over 1.16 times 1 over 0.82 versus 1 times 1 over 8.19 times 1 over 0.82. Well, notice they're both being multiplied by 1 over 0.82. So that last conversion really isn't necessary. You know, if I can figure out which of these is bigger in pounds, well, that one is also going to be bigger in dollars. So I don't need to convert to dollars. So that righty, just making that observation, I'm simplifying things. Now, which is bigger? 1 times 1 over 1.16, or what I have over here, 1 times 1 over 8.19. Well, notice 1 over 8, roughly, is a lot smaller than 1 over 1. Okay, so without even crunching these numbers, just by eyeballing it, it's quite clear that this value is going to be bigger, so that leads me to the correct answer of A for this one. Okay, so any take-homes from this? Well, keep in mind, if you have to convert units, start with what you are given, think about what you want, set up your unit conversion factors so that the units cancel in the proper way to give you what you want. And these unit conversion factors, they may be given to you in the form of a sentence. Maybe they'll actually give you the fraction. Sometimes they'll write it in terms of an equation, but ultimately you want to translate it to this fraction form, the units you want on top, the units you're trying to cancel on the bottom. And then before you, decide on your answer, cancel the units to make sure you're getting exactly what you want. And of course, if the numbers look really ugly, well, you might be in a position where you're just going to have to crunch the numbers. But in this case, taking a step back, thinking about it logically, we could see, oh yeah, A's definitely got to be bigger. And that's why, in this case, A is the correct answer. All right, great. Let's take a look at the next question. All right, let's take a look at this one. A fish tank has a length between 36 and 42 inches, a width between 12 and 18 inches, and a height between 18 and 24 inches. Which of the following could be the volume of the tank in cubic feet? We're told 1 foot equals 12 inches, and it says select all that apply. So there could be more than one that I need to choose to get this one right. Okay, so I'm asked to find the volume. So this is a tank with a length, a width, and a height. So I'll just remind myself it's some kind of rectangular solid, and the volume for that shape is length times width times height. Okay, now I notice it's asking for the volume in cubic feet. Okay, so I want to keep track of units as they're mentioning units. I'm sure those are going to be important. And now I notice that length, width, and height are given to me in terms of inches. Okay, so I'm not sure exactly how I'm going to want to go about my conversions, but I'm going to keep the units in mind. I want the final answer in cubic feet. I'm given length, width, and height in inches. Okay, and then now notice I'm not given a specific value for the length, I'm given a range of values. So let's see if I can come up with an expression to represent that to help me keep track of this information. So the length could be anywhere from 36 to 42, so I'll write that inequality. The width could be 12 to 18, and the height is between 18 and 24. Okay, so I suppose if I want to find all of the possible values for the volume, I should find out the biggest possible value, the smallest possible value, the biggest I get by multiplying all the largest possible length, widths, and heights. Same thing to get the smallest possible value. And then all the possible values will have to be somewhere in that range. Okay, so my first hesitation as I think about proceeding along those lines is I'm multiplying some pretty big numbers together. Okay, so and I also notice, well, this is in inches, right? Each of these is given to me in inches. So then I'm going to get an answer in cubic inches, and I have to convert that to cubic feet. Okay, so, at some point I'm going to need to do a conversion. So the question is, do I want to convert these to feet first? Or do I want to multiply them, get an answer in cubic inches, and convert from cubic inches to cubic feet? Well, let's think about it from a certain angle of how can I make my life easier in terms of arithmetic? Well, do I want to multiply big numbers together, which is what I'd be doing if I'm working with inches, or do I want to turn these into feet, which would be smaller numbers, right? 42 inches is some smaller number of feet, and then presumably the arithmetic would be easier. Okay, so my inclination is let's convert from inches to feet first. Okay, but just to kind of play the devil's advocate, what would happen if I did multiply these numbers out? Well, then I would get some big number for the biggest possible value, some smaller number for the smallest possible value, and then that would be in what unit? Well, inches times inches times inches, that would be inches cubed. And I'd get that for the biggest and the smallest. And then I'd need to convert to cubic feet. Well, how do you convert from cubic inches to cubic feet? Well, okay, I have this conversion factor. 1 foot is equal to 12 inches. But that would only cancel one of these inches, right? That wouldn't give me cubic feet, which is what I want. It would give me, well, inches squared times feet. Okay, so I need to do that 2 more times. So 1 foot over 12 inches, 1 foot over 12 inches. I need to do that 3 times in a row to get from cubic inches to cubic feet. So notice I'm having a really big number here already for x, and I'm multiplying by that 1/12 3 times. Okay, no thank you. That's too many big numbers for me. That really confirms I want to do it the other way. Okay, so let's convert. How do you convert from inches to feet? Well, I'm just going to write it out so that I convince myself I'm not making some kind of silly mistake. So I have 42 inches. I want to get to some number of feet. Okay, so if I multiply by feet over inches, 1 foot over 12 inches, inches cancel, I'm left with feet. Okay, great. So basically, I confirmed to myself I multiply by 1 over 12, or I divide by 12. So I can just divide each of these numbers by 12 to get feet. So 42 over 12, let's see, that's 3 to 36, and then another 6 on top of that, so 3.5. This is 3. Okay, there's my range of lengths in inches. Widths would be that. And, pardon me, I think I said that's the length and width in inches, but that's actually feet, right? We started with inches, we're converting to feet. Okay, then the height in terms of feet, there's my range there. Okay, so now I can ignore these inches, I can just use feet. These are much smaller, much nicer. Okay, so length times width times height gives me volume. 3.5 times 1.5, no thank you. How about 3.5 times 2? Okay, that's 7. Great. 7 times 1.5, well, that's just add 3.5 to 7. Okay, so my maximum is 10.5 feet cubed. That's my maximum volume. Do the same over here. 3 times 1 is 3. 3 times 1.5 is 4.5. Okay, so 4.5 feet cubed. All right, there's my maximum. There's my minimum. So pick all that apply. Okay, well, it couldn't be 4. It has to be, 4.5 is my minimum. So it could be 6, could be 8, could be 10. Okay, but 10.5 is my maximum. So it couldn't be 12, couldn't be 2 or 4. So that leads us to the correct answer on this question, C, D, and E. Okay, so any take-homes for this one? Well, more unit conversions. The goal there is always pay attention to the units. Make sure you're not forgetting that that's an important part of the question. And on top of that, think about, be strategic about when you do your unit conversions. If you're asked to calculate an area or a volume, you often run into the question, well, should I calculate the volume or area first and then convert, or should I convert each of the lengths and widths and heights or radii or whatever you're given? Should I convert those first and then calculate my area or my volume? And in this case, it was quite clear you want to convert from inches to feet first. It makes the arithmetic a whole lot simpler. And then again, that led us to the correct answer of C, D, and E for this one. All right, great. Let's take a look at the next question. All right. Working at their respective constant rates, machine A takes 3 hours to produce 120 cakes, and machine B takes 5 hours to produce 320 cakes. How many more cakes does machine A make in 5 hours than machine B makes in 3 hours? Okay, so I have machines working at different rates, producing different amounts of objects. So the equation that comes to mind is work equals rate times time. So notice, very similar to distance equals rate times time, except instead of trains traveling a certain distance, you have machines making a certain number of products. So work is the number of products that are being made. Rate, instead of being, miles per hour, kilometers per minute, something like that, it's going to be the number of products produced in a certain amount of time. Okay, so in this question, we're making cakes. So the unit for work is number of cakes. The time is given to us in hours. So I'd want my rate in cakes per hour. Okay, so how many more cakes does machine A make? Well, I guess we should figure out how many cakes machine A makes in 5 hours, how many machine B makes in 3 hours, and then we can compare them. Okay, so now I'm going to write a work equals rate times time equation for each of these machines because it may turn out that they have different rates. And if that's the case, I obviously couldn't use the same rate for both of them, so I'll need two totally separate equations. And notice another thing I'm doing, so I don't confuse my variables, is to not just say rate. Because if I said R, well, when I'm looking at my notes, 30 seconds or a minute later, I might ask myself, wait, was that the rate for B or for A? So I'm going to label each of them the work, the rate, the time. Specifically, am I talking about machine A or machine B? Okay, so how many cakes does machine A make in 5 hours? Okay, so the time for A is 5. We want to know how many cakes it's making, so I need to find out the rate for A. Okay, well, what am I told about A? Machine A takes 3 hours to produce 120 cakes. Okay, I guess I can use another work equals rate times time equation to see if that helps. So machine A takes 3 hours. Okay, so its time is 3. To make 120 cakes, okay, so the amount of work is 120. Okay, great. What's missing is the rate. I can solve for rate. And it tells me that they're working at constant rates. So that rate isn't going to change. So if I calculate it for this 3-hour scenario, it'll be the same later on too. Okay, so I solve for rate A. I get that's 40 cakes per hour. Okay, great. So I can plug in 40 there. I get machine A makes 200 cakes in 5 hours. Okay, same process for B. Well, it's working for 3 hours, so the time is 3. I want to figure out how many cakes it makes. We're told that machine B takes 5 hours to produce 320 cakes. Okay, so I'll get another work equals rate times time equation to figure out the rate for B. So 320 cakes total equals the rate of B times 5 hours, they say. Okay, so 320 over 5. So 5 times 60 is 300. Another 4 will give me 20. So the rate for B is 64 cakes per hour. Okay, great. I can plug that in. 64 cakes per hour. That's times 3 hours. So that's 180 plus 12. So that's 192 cakes. Okay, so now I'm asked machine A makes how many more cakes in this amount of time? So, well, machine A made 200, machine B made 192, so A makes 8 more cakes than machine B. So that leads us to the correct answer of A for this one. Okay, so any take-homes? Well, when you're working with machines that are producing different amounts of products, it's kind of like a D equals RT question like we've been doing previously, but in this case, instead of distance, use work. Okay, and as always, keep track of your units. Is it per minute? Is it per hour? Sure, it didn't switch up on this question, but it could happen, so I was careful to note, okay, hours, cakes per hour, etc. And finally, note when you have two different machines, well, often they're going to have different rates, and if that's the case, you're going to have separate equations for each of them, and I'd recommend that you keep track of your variables with subscripts so you know which machine exactly you're talking about. Are you worrying about the rate for machine A or for machine B? Do yourself a favor and you can write these subscripts so that you don't confuse your variables at some point. Okay, so following all those steps, that led us to the correct answer of A for this one. Okay, great. Let's take a look at the next question. Alright, let's take a look at this one. One machine can make C chocolate bars every 2 hours. Another machine operates at 1/3 the speed of the first machine. How long will it take both machines operating together to make C chocolates? Okay, so just like in the last question, we have two different machines. So when that's the case, we want to have a different work equals rate times time equation for each of them. In this case, we know that they're going to have different rates. So it wouldn't make sense to have the same equation if you have two different R's. Okay, so that's one point. Another is, notice in this problem, they're working together, these two machines. Okay, in the last question, they were working separately, doing their own thing. Here, the machines are operating together. So whenever that's the case, it's good to know that you can add the rates of two or more machines to get the overall rate. Okay, and that's such an important point, I'm going to write it down here. You can add the rates of two different machines or two or more machines working separately to get their overall rate, the total rate. So R here is the rate of these machines working together, or the total rate. RA is the rate of machine A working on its own. RB is machine B working on its own. If there are more machines, I could add those two to get the total rate. Okay, now another point, well, when you have different machines, and especially when they're working together, I like to have a chart to help me keep track of what variable relates to what machine and how can I relate those different variables together. So I'll write work equals rate times time at the top. Then I've got a column for work and rate and time, and then I've got a row for each machine. Okay, and that helps me keep track of, okay, when I get a rate, is it machine B's rate, is it machine A's rate, is it the total rate? This chart helps me keep track of that. And it's also a nice way to stack up your variables so that you can say, all right, I can add, let's say, the rate for machine A and the rate for machine B, and if I add those, I'll get the total rate, or the rate of them working together. Now, another important point, you can add the rates if machines are working together, but you can't add their times or their works necessarily. Okay, the rate, their times working separately, if you add those, that's not going to give the total rate. Okay, pardon me, it's not going to give the total time if you add their times separately. But if you add their rates working separately, again, yes, that gives you their total rate, the rate of them working together. Okay, so in this question I'm asked, how long is it going to take both machines operating together to make C chocolates? Okay, so working together, that's this row right here. They're making C chocolates. I want to know how long it's going to take. What's the time? Okay, so if I found the rate of them working together, I could solve for the time. To find the rate of them working together, I need to find the rates of them working separately. All right, so I'm told machine A can make C chocolates. Okay, so machine A, the work is C every 2 hours, so the time is 2. All right, great. So I can solve for the rate for machine A. C, or work, equals rate A times time, or 2. So the rate for machine A is C over 2. Okay, I'll punch that into my chart. Another machine, I'll think of that as machine B, operates at 1/3 the speed of the first machine. Okay, so the rate of machine B is 1/3 the rate of machine A. Machine A is C over 2, so the rate of machine B is 1/3 of C over 2. In other words, C over 6. All right. So I can now punch in the separate rates for each machine. I know if I add those together, I'm going to get the total rate. So C over 2 plus C over 6 is equal to the total rate. So 3C over 6 plus C over 6 gives me 4C over 6, or 2C over 3. Great, I found the rate of the machines working together. Okay, so now I have those two columns filled in, and I can solve for the time when they're working together to produce C chocolates. So C equals 2C over 3, that's the rate, times time. Okay, to solve for time, I guess I'll multiply by the reciprocal of this fraction. So that'll get rid of the fraction and help me isolate t. So multiply both sides by 3 over 2c. Okay, so it goes away on this side. Over here I have 3 over 2c times c. Okay, well, the c's cancel, and I'm left with 3 over 2. That's the time it takes for them working together to produce C chocolates. Yes, that's what they were asking for. So that leads me to the final answer of C. Okay, so any take-homes from this question? Well, this equation, very key when you have machines operating together. The rates of the machines working separately can be added to get their total rate. And this chart can help you keep track of the rates and the work for the different machines and kind of set you up nicely to add the rates to get the total rate. Okay. I also, again, like to keep track of my different rates with subscripts A and B. That way I don't at some point see an R on my page and wonder, wait, which machine does that connect with? I always know exactly what the information I've written down, what the variable stands for. Okay, great. So following all that stuff, I get to the correct answer on this one of C. All right. So before we look at the next question, a warning about the next two problems we're going to encounter. So the ones we've done so far, all pretty much fair game for the GRE, both in terms of the content they're covering, but also the level of difficulty. For the last two questions, we're going to bump up that difficulty level, and they're going to be harder than anything you're likely to see on the GRE. So I would take them in that spirit. They're a good opportunity to work through some of these concepts, a way to challenge yourself, but I wouldn't worry too much if you get stumped on these. On the other hand, when you look at the explanations, if you're able to engage with the concepts, if you're able to kind of follow the solution as we go through it, then you'll be in good shape. All right, so with all that in mind, let's take a look at the next question. All right. So before we dive into this question, just a reminder about the disclaimer for question number 7, this question, and question number 8, the next question. So until now, all the questions we've done, questions 1 through 6, have all been fair game for the GRE in terms of the content they cover and the difficulty level. For question 7, for this question and for the next question, question number 8, we're going to bump up the difficulty level so that they're probably more difficult than anything that you're likely to see on test day on the GRE. So if you struggled with this one, if you struggle with question number 8, the next one, I wouldn't worry about it too much. As long as you're able to engage with the general concepts, follow the explanations, you should be in good shape. All right, so with that in mind, 1 chlorine tablet will purify p cubic feet of water. How many tablets will be required to purify a cylindrical tank with a radius of r inches and a height of h yards? And we're told 12 inches is 1 foot, 3 feet is 1 yard. Okay, so I want to know how many chlorine tablets I need to purify a certain amount of water. And I'm given all these units, so I'm thinking about units for this question, and ultimately I want to find tablets. So what am I told about these tablets? Well, 1 tablet, so I'll say 1T, will purify p cubic feet of water. Okay, so tablets is on top, that's great. How do I get tablets by itself? Well, if I could multiply this rate, 1 tablet per p cubic feet of water, by a certain number of cubic feet, the number of cubic feet in the tank, I'll just call that x cubic feet or x feet cubed. Well, feet cubed should cancel, and that should give me the number of tablets I need. So what is x? Well, x is the number of feet cubed in the tank. Okay, so that's my goal. How many feet cubed are in this tank? Well, okay, it's a cylindrical tank, so the volume of a cylinder is equal to pi times the radius squared times the height. Okay, now I want this volume in feet cubed. So I want to make sure that I have the radius in feet and I have the height in feet so that I end up with feet cubed. Okay, so what is the radius? Well, the radius is r inches. So I need that to be in feet though, right? If I just plugged in r, and notice my answers are all in terms of r, so I can't actually plug in a number, I just have to plug in r. But if I just plugged in r, it would be in inches. So I want to convert inches to feet. Okay, so how do I do that? Well, start with what I'm given, r inches, and I want to get to feet. Okay, so r inches times, well, I want feet over inches, right? If I want the inches to cancel and to end up with feet, and I know that there's 1 foot and 12 inches. So r inches is basically equal to r over 12 feet. Sound good? The inches are canceling, and I'm left with feet. Okay, great. So the radius is r over 12 feet. That's a start, because it's the radius squared that I need. What about the height? Well, let's go through a similar process. Okay, I'm given h yards, but I want feet. So how many feet is h yards? Well, let's write a conversion factor. I want to get rid of the yards, so I'll put that in the bottom. I want feet, so I'll put that in top. I know there's 3 feet in every 1 yard. Yards cancel. So h yards is equal to 3 times h, or 3h feet. Okay, great. So I have my radius, r over 12 feet. I have my height, 3h feet. I can plug that in here. Okay. So v equals pi r squared h. So v equals pi, r is r over 12 feet. That's being squared. Then times the height, which is 3h feet. Okay, multiply this out. I get v equals pi times, well, r is in the top, it's squared. 12 is in the bottom. 12 squared is 144. Okay, that took care of this. That's going to give me feet squared. Then times 3h feet. Yes, that'll give me feet cubed. So that's times 3h. Okay, now can I simplify this at all? Well, 3 into 144. I believe that's 48, right? 3 times 40 is 120, plus another 24 on top is 144. Okay, so I'll simplify this to pi r squared over 48 is the volume. Now, remember at the beginning we said what we're looking for is the number of chlorine tablets we need to purify a certain amount of water. We know 1 tablet will purify p feet cubed. So if I multiply by the number of feet cubed in the tank, that'll give me the number of tablets I need. Okay, so, and we found that here. This was the volume of the tank in feet cubed. So I'll copy that up here, times pi r squared h feet cubed over 48. Okay, now they're asking for the number of tablets, so let's see if the units work out. Feet cubed in the bottom, feet cubed in the top. Great, I have, what am I left with? Tablets. Okay, so my final quantity, I'll just copy it down so that it looks a bit more neat. In the top, I have pi r squared h, and in the bottom, I have 48p. Okay, what about this t? Well, this t was just a unit. You know, it's kind of like feet or yards. In this case, t was tablets, so that's the quantity of tablets I need. Okay, so let's see, is there an answer choice that looks like that? H r squared pi, yep, that's what I have in top, over 48p, yep, that's what I have in the bottom. So all of that led us to the correct answer for this one of B. Okay, so any take-homes for this one? Well, this one, it's really all about units, okay? Thinking about the units of what I'm asked for ultimately, number of tablets. The units of what I'm given. Well, I'm given the number of tablets for a certain amount of cubic feet of water. So somehow I need to multiply that by the cubic feet I'm actually interested in to cancel the cubic feet, get the number of tablets I need. Now the other wrinkle was, well, I can't just calculate the volume of the tank in cubic feet given the variables as they're presented. Those variables are presented with inches and yards, so I need to have another step of converting those units into feet. Okay, so I write out my conversion factors. I convert inches and yards both to feet. I plug all that in. I go back to the original step of multiplying the tablets per feet cubed by the feet cubed of the tank overall. And that gives me the number of tablets I need to purify this tank. All right, great. Let's take a look at the next question. All right, let's take a look at the last question. Pumps A and B working together can fill a swimming pool in 7.2 hours. Pumps B and C working together can fill the pool in 12 hours. And pumps A and C working together can fill the pool in 9 hours. How many hours would it take pumps A, B, and C working together to fill the pool? Okay, so like some of the previous questions we were discussing, this is a rates question. We have different machines working at different rates to achieve a task. So I'll say I want the equation work equals rate times time. Now, what's the work in this question? Well, we're not producing cakes, we're filling pools, so I could say, I guess, the number of pools filled, that's my work. Okay, what's the rate for the different pumps? Well, we're filling pools, so I could say it's the number of pools filled. And what's the time? Well, it's given in hours, and the time is just hours. So those units work out. Number of pools filled per hour times hours give me number of pools filled. Okay, now, like another question we were working on together, we have different pumps all cooperating, all working together to fill the pool. So when that's the case, remember, if you add the rates of machines, if you add their separate rates together, you can get the overall rate when they work together. So the rate of machine A, or in this case pump A, plus pump B, plus the rate of pump C, gives me the rate of all of them working together. And what I want to know is how many hours, or what's the time, to fill one pool when they're all working together. Okay, so let me plug that into this equation here. So the work, okay, we're trying to fill one pool, so 1, equals the rate. Well, they're all working together, so the rate total, RT, would just be RA plus RB plus RC, and then times the amount of time. And that's what they're asking for. What is time? Okay, so we know the work, one pool. If we could figure out their combined rate, the rate when all of them are working together, then I could solve for t. Okay, so let's see what info we're given. Well, when A and B are working together, they can fill a swimming pool in 7.2 hours. Okay, so this is A and B together. Okay, now notice I'm being careful to label the rates separately, and as I'm working through this initial first sentence here, I'm reminding myself, what's the scenario I'm talking about? This is A and B working together. Okay, so when A and B are working together, and I'll just have like a work equals rate times time equation, working together, they can fill one pool, so the work is 1. They can do it in 7.2 hours. Great. And that's the rate for RA plus RB, those two working together. Okay, so the rate of A plus B working together is just 1 over 7.2. Okay, so I could go through the exact same process for the remaining information. Pumps B and C working together can fill the pool in 12 hours. So this would be 12, it would be B and C. So the rate of B plus the rate of C would be 1 over 12 by following that exact same process. And let's do that for A and C working together. So for the rate of A plus the rate of C, they tell me that's 9 hours. Okay. So I would plug in 9 over here. This would be rate of A plus rate of C. I could solve for rate of A plus rate of C and get 1 over 9. Okay, so now I want the rate of all three working together. And if I can get that, I could solve for time. So I've got 3 different equations here, 3 different variables. So I suppose one solution path would be, okay, maybe I could start substituting, right? I could find the rate of A in terms of B, and then I could plug that in here. And then I could find the rate of C in terms of B, and I could plug that in here. And so maybe I could arrange them so that I get everything in terms of, one of the rates. This equation, maybe I could get it in terms of RB by substituting intelligently. And then I could solve for RB, and then I could plug that in here and solve for RC, etc. Okay, so that's a viable solution path in a sense. I mean, I'm pretty confident that I could do that and get to a right answer, but I have some hesitation because that seems like a whole lot of algebra. Okay, so I'm going to think, are there any other ways I can use this information? Any other ways I can work with those equations to arrive at the rate, the combined rate, RA plus RB plus RC, right? So, well, my first solution path was kind of assuming that I want to solve for these separately, right? Solve for RB first, then solve for RA, and then solve for RC, etc. But notice, I don't necessarily need to find them separately to get the answer. I just need to know that they are all added up. So could I start adding these up? What would I get? Well, if I add these first two, I get the rate of A plus the rate of B plus the rate of B plus the rate of C. Okay, so that would be, I'll write it over here, RA plus 2RB plus RC. Okay, that's not too great because there's a 2RB there, although it seems like it's sort of heading in the right direction. What if I add this on top of it, RA plus RC? Okay, so if I'm adding them all together, I get 2RA plus 2RB plus 2RC. Okay, and then I could get some number there, some quantity. Okay, great. Now that's looking pretty close to what I want. If I could just divide that by 2, divide this whole expression by 2, that would give me RA plus RB plus RC, right? I could say multiply this whole thing by 1/2. All those 2's would cancel. I just need to make sure I multiply the other side by 1/2. Great, that'll give me their combined rates. I could plug that in here. I could solve for t. Okay, so what I did to get this was I added all these equations, so I have to add all these fractions. Okay, well, some annoying arithmetic there, but I think that sounds preferable to me than trying to solve for b individually. That's just too much algebra, too much arithmetic. I can live with this. Okay, so common denominator for 12, 9, and 7.2. It's another challenge. Okay, do they all go into 12 times 2? 24. No, 9 doesn't go into 24. What about 12 times 3? 36. Yes, 9 goes into 36. 9 times 4. What about 7.2? Well, if I multiply that by 5, 7 times 5 is 35. That's pretty close. But then there's a 0.2 times 5. That gives me the extra 1. Okay, great. So these all go into 36. All right, so 1 over 12, I'd multiply by 3 over 3. I get 3 over 36. 7.2, I'd multiply by 1 over 7.2, I'd multiply by 5 over 5. I get 5 over 36. This I'd multiply by 4 over 4, get 4 over 36. Okay, if I add all those up, I get 5 plus 3 plus 4, so that's 12 over 36, or 1 over 3. Okay, so remember, that's to get 2a plus 2b plus 2c, right? That's going to be equal to 1 over 3. But I want just plain old RA plus RB plus RC, right? I don't want these 2's in front, so I'll multiply this whole thing by 1/2, or in other words, multiply both sides by 1/2. All those 2's cancel. 1/3 becomes 1/6. Okay, great. So I can substitute RA plus RB plus RC is just equal to 1 over 6. So 1 swimming pool times 1 over 6 swimming pools per hour times t hours. Solve for t, I get 6 hours. Okay, great. And that leads me to the correct answer for this one of D. All right. So any take-homes for this question? Well, it's similar to the concepts we've been working with, right? You have machines that have their own separate rates, but they're working together. And the key there is, well, if you add their separate rates, then you get their total rate. Then you can use this work equals rate times time equation and work your way towards an answer. Now, I think the twist in this equation, what made it especially difficult, this question, was that, well, the algebra to solve for RB and RC individually, probably not feasible to do on an actual GRE. You know, maybe you could get away with it if the numbers were simple enough, but it's pretty tough here. So what made this one tricky was, can you see this very efficient path of adding their combined rates to get some larger equation which you can divide by 2 and solve directly for the combined rate of RA, RB, and RC. So put another way, we stayed flexible. We didn't assume from the outset one particular path that we need to solve for the individual rates. We played around with the algebra, worked our way to an efficient solution. Okay, turns out that these fractions all add together pretty nicely. As long as I was careful along the way, checked my work, made sure I was solving for exactly what I wanted, I'm in good shape. Okay, all of that leads me to the correct answer, again, of D. Alright, thanks so much for watching our GRE video on conversions and rates. I hope you found it helpful. And in addition to the math content we covered, I'd keep in mind a few pointers. Well, first, when you're reading through a GRE question and you notice units, inches, or feet, or yards, or miles, you want those to jump off the page. There's a good chance they're going to be pivotal to the solution of the question, so you want to make sure you don't accidentally gloss over those. Now, when it comes to rates questions, your goal is, can I translate this language into algebra? Often a very helpful step. Keep the different variables distinct. If you're doing all that stuff, you should be in good shape. All right. Well, thanks again for watching. Happy studying, and I'll see you next time.